Hi, physics. This is Mr. Janowski. And look, I have a new toy. So I got a new microphone. If anyone's interested in gear, this is the Audio Technica AT 2005 USB. So I did a few tests, and the audio seems to be much better than the little clip-on mic that I had on top of my laptop screen, which even that I thought was a big improvement over just the built-in mic in my MacBook. So hopefully this sounds better. So let's continue with the slides. So this is part 5. Last part was a bit of a history lesson, and yeah, we'll keep going. So, to review what we did last time, who had a fake nose, a moose with a drinking problem, a knack for making extremely accurate measurements of the positions of the planets, and died from holding in his pee for too long? This would be Tycho Brahe. So, if you haven't watched the little SciShow video on his life, please go back and watch that. He is just a fascinating person. Second question. That should be who? Who was Tycho Brahe's assistant, who used his data to formulate 3 laws of planetary motion? That was Johannes Kepler. Also a very important, probably more important than Tycho Brahe ultimately, just not as colorful a person. And finally, who wrote Principia and was probably the greatest scientist of all time? This would be our old friend, Isaac Newton. So let's do a quick review of Kepler's 3 laws of planetary motion. So the first law, also called the law of ellipses, says that planets follow elliptical orbits with the sun at one of the focuses of the ellipse. So everyone up to this point thought that the planets moved in circular orbits. Technically, some people thought that the planets were orbiting the Earth instead of the sun, which is wrong. No, the planets were orbiting the sun. But people, for kind of vaguely philosophical reasons, all thought, well, circles are the perfect shape, so the planets must be doing circular orbits. Turns out they're not. They're doing elliptical orbits. And the sun, if you look at the picture, is not at the center of the ellipse. So right here would be the center of the ellipse. The sun is actually at one of the focuses of the ellipse, also called foci, one of the foci of the ellipse. And at the other focus, you have nothing. So, yeah. That's the first law, the law of ellipses. The second law is the law of equal areas. So I'll try to do this quickly. Yeah, just remember the idea that if we had 12 equal months in every month that the Earth did its orbit around the sun, it would sweep out equal areas. So the area of this pie piece right here is the exact same area as all of the other pie pieces, even though they have different shapes. Some of them are very long and thin on the ends. This first one, January to February, is kind of stubby, but very long along the back end. Yeah, they all have the same area. That's what you get in the picture. If you look at the GIF, what you can see is, why this works, is the Earth moves very slowly in its orbit when it's far from the sun, and when it's closer to the sun, it moves much quicker. So if we're looking at this picture is certainly not to scale in a couple of ways. The Earth's orbit is much bigger than that. The Earth is much smaller compared to the sun than that. And also, the Earth's orbit is not nearly this elliptical. It's really very close to being a circle, but it is an ellipse. It's just a barely elliptical ellipse. Planets move faster when their elliptical orbits bring them closer to the sun. This is the law of equal areas. And then we get to the mathy one. So this is Kepler's third law, also called the law of periods. So this says the planets that orbit closer to the sun move faster. So if you're looking at this GIF, the inner planets, Mercury and Venus, you can see how quickly those guys are going along. And if you go to the outer planets, so Jupiter, Saturn, Uranus, and Neptune, these guys all out here, they move way slower. And it turns out Kepler discovered that there is a mathematical relationship between the cube of the semi-major axis, which is basically the radius. It's the long radius of an ellipse. So the cube of the semi-major axis compared to the square of the orbital period. So the period is the amount of time it takes for the planet to do one orbit. So for the Earth, that's 1 year. That's what a year is. And the semi-major axis is it's essentially the radius, because all the planets, even though they're going in ellipses, they're really close to being circles. So think of it as the longer radius of an ellipse. And so, yeah, there's this mathematical relationship. So the top version, this is the ugly version. You can use this if you want, but I would actually recommend using this bottom version, which is the exact same thing, only I've squared both sides, which makes this easier to get into the calculator. So Kepler's third law, the law of periods. So think back to chapter 9. What is the formula for gravitational potential energy that we learned in chapter 9? That is GPE is equal to mgh. So yeah, that worked in chapter 9, and it's not going to work in this chapter. So that law that we used, that formula that we used, only holds when you're relatively close to the surface of the Earth. So remember, when you're dealing with a sphere, you treat all the masses if it's at the center, and you measure your distances from the center of the sphere. So what that means is if you're standing on the surface of the Earth, you're essentially one Earth radius away from the center of the Earth. If you go up 10 meters, 100 meters, even 1,000 meters or so, you're not getting that much further away from the center of the Earth. So your distance from the center of the Earth basically stays the same. It does change a little bit, but it's a very tiny change compared to the radius of the Earth. So yeah, you can use that one, the chapter 9 formula, GPE is equal to mgh, only if you're really close to the surface of the Earth. But gravity is going to get weaker as you get further away. Remember the formula for the force due to gravity. F sub g is equal to big G m1 m2 over the distance between the things squared. So gravity will get weaker as you start to get far away. If we're dealing with things like rockets and satellites and comets and moons and planets and other things, you can't assume that your distance to the center of the object, to the center of the planet you're measuring from, is essentially constant, because it's not going to be. It's going to vary tremendously. So here is our new formula for GPE. This is the one we're going to use in this chapter. So this one is GPE is equal to negative big G m1 m2 divided by d. So a couple of things to point out. We have a minus sign out here, which means GPE is always going to be negative because these other numbers are all going to be positive. So positive times positive times positive divided by positive gives you a positive number, but we have this minus sign out in front. So our GPE will always be negative. And notice that GPE varies with the inverse of d, not with d squared. So if this were a d squared, this would be, and there were no minus sign, this were a d squared, this would be our formula for force due to gravity. So why I'm pointing this out is this looks a whole lot like our formula for the force due to gravity, also called the law of universal gravitation. It's just very slightly different. So it's very easy to mix it up. So be careful and always grab the right formula. So what is going to happen to the value of GPE when the value of d gets very big? So when the distance involved between the two things starts to get very big. So we're looking at the behavior of this function. So as the distance, which is in the denominator, starts to get very big, we're going to keep dividing by a larger and larger number, and that means GPE is going to get very small. So GPE is going to get closer and closer to 0, and it's always going to remain negative. If you are infinitely, in scare quotes, infinitely far away from a planet, your GPE is 0. So why is that in scare quotes? Well, you can't actually be infinitely far away from anything, but you can be so far away from a thing that you might as well call it infinity. It makes the math easier to do, so you call it infinity, and you get an answer of 0. So yeah, here's that idea, kind of explained mathematically. So what happens to the value of GPE when the value of d gets very big? GPE gets closer and closer to 0, but always remains negative. If you are infinitely far from a planet, your GPE is 0. So this is not very rigorously written mathematically. It should say something to the effect of limit of GPE as d approaches infinity. But we're physicists. We like math, but we don't love it. So I just wrote it kind of the lazy, sloppy way. This should make someone in the math department a little upset if they saw it this way. But anyhow, the key idea here is anything finite divided by infinity equals 0. So big G times mass of one object times mass of the other object, it's going to be some finite positive number. And then if we're so far away, if the two masses are so far away from each other that we're basically dividing by infinity, we're going to get zero. So that's how this works. So why do we treat GPE as if it's negative? So if you are near a massive object like the Earth, you have to add energy to get away from it. In a sense, you owe energy. So the Earth kind of has you trapped. You're in a gravitational potential well, is one way a physicist might say it. And if you want to get infinitely far away from the Earth, you have to put energy in. You owe energy. It's like a debt. So here's a graph that's showing us GPE as a function of distance. So if you're, on the surface of the Earth, you owe this amount of GPE. You have this fairly large negative number of GPE. If you're starting further and further away, well, the gravity of the Earth isn't affecting you as much, so you owe less energy to get away from the Earth. So, yeah, a mathematician would say we're looking at the behavior of the function, and so would a physicist for that matter. So what is the GPE of a 10 kilogram mass sitting on the Earth? Well, here's our formula. So we're going to plug in the numbers. Don't forget the minus sign. You'll lose half a point if on the test if I ask you for GPE and you neglect the minus sign. So you plug in your value for big G, the mass of the first thing, the mass of the Earth, divide by the radius of the Earth, because again, this is a sphere, and we measure our distances from the center of the sphere. So from the center out to here is 1 Earth radius, and you get this number. So a fairly large negative number, minus 6.25 times 10 to the 8th joules. So that's negative 625 million joules. But remember, joules are small, so that's okay. We can have big numbers for this. So what if the mass were 1 Earth radius above the surface? So instead of being right here on the radius of the Earth, we are 1 Earth radius away. So we're starting off somewhere like this distance. Well, you would use the exact same formula, only the distance, in this case, again, because we measure from the center, would be 2 Earth radiuses. So that's why the 2 shows up here. Because your distance from this point, I should probably have indicated this with a little point on the drawing, your distance from the center would be 1 Earth radius to get to here, and then another Earth radius to get down to the center. So we get this number, which is, half the size of this one and still negative. And what if the mass were infinitely far away? Which again is impossible to be infinitely far away, but you can be really, really far away. Maybe we're all the way out at the Kuiper belt, so out, way out close to the edge of the solar system. So we're so far away that the Earth barely has any effect. What is the GPE going to be? Well, you just plug in infinity for down here. So negative something times something times something divided by infinity. Well, you're dividing a finite thing by an infinite thing, so you're going to get 0. Let me point this out here. If you pick up your calculator and you try to do this math and you look for the infinity button, you're not going to find one. There is no infinity button. Infinity is not actually a number. Infinity, it's more like a direction. It just means more. You treat it like a number. So just get used to this piece of math. Anything finite divided by something infinite is going to give you 0. So if we have a 10 kilogram object and it is released so far away from Earth that it is essentially infinitely far away from Earth, gravity slowly attracts it towards the Earth. How fast will it be moving when it is 1 Earth radius above the surface? And how fast will it be moving when it hits the surface? So what big one with everything kind of idea can we use to solve this problem? Well, remember chapter 9, we can use the conservation of energy. So we would do this just like any other conservation of energy problem. So how fast will it be moving when it is 1 Earth radius above the surface? So you would write, in my slides, I skipped step 1, the sketches and all that stuff. And here we are on step 2, the law of conservation of energy. So we'd look and consider what kind of energy you have at the beginning. So maybe there's kinetic energy initially, maybe there's GPE initially. There's no external work. We're not dealing with friction or air resistance or anything like that. And then at the end, we have kinetic energy and we have GPE. So initially, this thing is released. It's not moving, so it has no kinetic energy. And it's infinitely far away, so it has no GPE. and the work again is going to be 0. So we just have 0 plus 0 plus 0 at the beginning. At the end of this situation, when we're 1 Earth radius above the surface, it's falling towards the Earth, so it is moving, so there is kinetic energy, and it is some non-infinite distance away from the Earth, so there's going to be some GPE that is owed. So I took this math, subtracted negative GPE to the other side, did some algebra to solve this for V final. So you might be a little worried at this point that I'm going to be taking the square root of what looks like a negative number, but remember, it's not going to be a negative number because my GPE is going to be negative. So negative times a negative will give me a positive. So we'll get the square root of a positive number. So you do all this stuff, and you get a fairly big number, 7,912 meters per second for our final velocity. So that's about 8,000. Did I say miles per second? Meters per second. This is about 8,000 meters per second. So bloody cheetah, that's about 16,000 miles per hour. So that's obviously very fast. Does that make sense? It actually does, because we're dealing with big astronomical things, and we're falling astronomical distances towards the Earth. So it is reasonable that if you drop something from way out in the Kuiper belt and it just let it fall towards the Earth, it's going to take a while to get there, but eventually it will. And when it does, it'll be moving pretty fast. So the second part, how fast will it be moving when it hits the surface? So same kind of math. I would recommend starting this not when you're 1 Earth radius above the surface. Start this again when you're at the Kuiper belt, because it makes your math easier. So no kinetic energy at the beginning because we're not moving. No GPE at the beginning because we're infinitely far away. No work being done. And then at the end, we're moving and we're close enough to the Earth that we have to consider GPE. So same math, plug in the stuff, you get a number. And this time you get 11,180 meters per second as our V final. Remember this number. This number will come up in slides in the future. 11,180 meters per second. So to review quickly, what is our new formula for GPE? Well, our old one was GPE equals mgh, but that only works when you're very close to the surface of the Earth. When you're dropping things off of buildings and hopping up and down in the air and playing with pogo sticks and things like that. If you're dealing with rockets and planets and asteroids and things like that, you've got to use this version. So GPE equals minus big G M1 M2 divided by R. To be consistent, I should probably call this D. Some books would always call this R. It's a distance. I should call it D. So what happens to the value of GPE when the distance R between the objects gets very large? Again, I should have switched to calling that D. Oh well, you'll survive. So when the distance between the objects gets very large, which is to say, as the distance between the objects approaches infinity, GPE is going to approach 0. So if you're infinitely far away, what's the GPE between the two masses? It's 0. And flashback to chapter 9. What is the formula for the conservation of energy? This is very much a one with everything idea. Sigma E initial plus sigma W external equals sigma E final. Sum of your initial energy plus sum of your external work equals the sum of your final energy. So you'll need that idea when you're doing homework problems and test problems in this chapter. So that's it for this part. Hopefully you found this interesting and clear sounding, because I like my microphone. I hope it sounds better.